Everything started from a single point, a point of impossible density. That's the beginning, the complete timeline of the universe, from the Big Bang all the way to heat death. And by the end, you'll know the whole story, from that first spark to the final silence. So we'll trace it, how a moment of infinite heat gave birth to every galaxy, every star, every planet. And then how the cosmos grows cold, how it grows dark, what triggered the beginning of everything, and what the last star will see before it winks out. This journey, it stretches across trillions of years. It connects your existence to the grandest scale, the largest scale imaginable. What does it feel like to know the ultimate fate of everything? Everything was in that first point. All the matter, all the energy, everything that would ever become us, or the farthest star. It was all packed into a space smaller than an atom. The whole cosmos was there, just in potential. That's the singularity. It's a boundary, a place where our understanding just stops. The ideas of before and after, they lose their meaning there. Because time, the way we know it, it didn't exist yet. There was no space for an explosion to happen in. There was just this state, this impossible state of infinite density and infinite heat. So the Big Bang wasn't an explosion into emptiness. It was the expansion of emptiness, of space itself, suddenly stretching and cooling from that one point. Stephen Hawking said, asking what came before the Big Bang is like asking what's north of the North Pole. The question might not have a framework. That moment, time zero, it's the horizon. The equations of physics break down there. They dissolve. What triggered it? Was there a cause, or does causality start right there? We stand at that edge. Looking into a past so complete, our language can't touch it. But from that origin, the unknowable one, a story starts, written in the cooling fabric of everything new. From that point we can't see past. The first moment happens. A stretch of time so short you can't really picture it. That's the Planck epoch. It goes from the very start to 10 to the negative 43 seconds. To get a sense of that, if you wrote a 1 and a decimal point, you'd need 42 zeros before you could even put the first number of that time down. In that one instant, the whole universe is tinier than any particle we know, but it's not nothing. It's all energy, pure energy. The heat is beyond any number that makes sense. And the four forces, gravity, electromagnetism, the strong force, the weak force, they aren't separate yet. They're one thing, a single force. In that place, space and time don't work like we know them. They don't run smooth. What you get instead is called quantum foam. Reality isn't a flat sheet. It's more like a bubbling sea, little fluctuations popping up. Tiny wormholes might appear and disappear. Little universes could form and then vanish. That's as far back as our physics can go. It's named for Max Planck. To go back any further, to see the very first instant, we'd need a theory that puts quantum mechanics and gravity together. We don't have that, so the Planck epoch is the edge. But even in that chaos, something is starting to shift. That perfect symmetry, that one force, it's about to break, and when it cracks, that's when the universe really starts. That perfect symmetry couldn't hold. The universe kept expanding, cooling past that impossible heat of the Planck epoch, and the first separation happened. Gravity peeled away. It became its own distinct force, the force that sculpts galaxies, that bends light, and it left the other three, electromagnetism, the strong nuclear force, the weak nuclear force, still locked together. That was the era of grand unification. For a sliver of time between 10 to the negative 36 and 10 to the negative 32 seconds, the cosmos was governed by a single set of rules. For everything except gravity, but that moment ended, and it ended dramatically. Something in the fabric of that early universe shifted, a field physicists call the inflaton. And when it shifted, it released a staggering amount of latent energy. This energy didn't create matter, it didn't create light, it did something more profound. It caused space itself to stretch, not just expand, to inflate exponentially faster than the speed of light. Think of a tiny, crumpled piece of paper, wrinkled with random folds and creases. Now imagine blowing that paper up to the size of our entire planet in an instant. All those wrinkles, all those sharp folds, they become impossibly smooth. The surface looks flat. That's cosmic inflation. In less than a blink so fast it defies comprehension, the observable universe grew from smaller than a proton to the size of a grapefruit. And this furious stretching did three critical things. First, it ironed everything out. It took any wild irregularities, any huge temperature differences, and stretched them so thin the cosmos became remarkably uniform. That explains why the cosmic microwave background, the afterglow of the Big Bang, looks almost exactly the same in every direction. Second, it made the geometry of space flat on the largest scales. And third, and perhaps most magically, it didn't make things perfectly smooth. On that quantum scale, tiny fluctuations were frozen into the fabric of space as inflation ended. Those microscopic ripples stretched to cosmic proportions became the seeds, the gravitational seeds for everything to come. Every galaxy cluster, every spiral arm, every star, every planet traces back to those quantum whispers amplified by inflation. Alan Gough's idea didn't just explain the smoothness we see, it gave us a reason for the structure we live in. This explosive beginning set the stage. And then, just as suddenly as it started, inflation ended. The inflattened field decayed. It dumped its remaining energy into a hot, dense soup of particles. And the universe settled into a more familiar, slower expansion, ready for the next act. Inflation ended, and the universe was left simmering. It was this broth of pure energy, a cauldron so hot that the basic ingredients of matter couldn't stick together. That was the Quark epoch, a fleeting era of chaos. For the first millionth of a second, the temperature was in the trillions of degrees. At that heat, the building blocks we know couldn't exist as stable things. Instead, space was filled with a seething, opaque soup, a quark-gluon plasma. Quarks, the particles that would later make up protons and neutrons, they zipped around freely. They were bound by gluons, the carriers of the strong force, but the energy was just too high for any lasting bonds to form. It was a constant dance. Creation and destruction. For every quark that popped into existence, an antiquark, its mirror opposite, would appear alongside it. They'd whirl through the plasma, meet their counterpart, and annihilate in a flash of energy. Then the process would begin again. This isn't just theoretical. In places like the Large Hadron Collider, scientists recreate microscopic versions of this state. They smash heavy nuclei together at nearly light speed. For a fleeting instant, they produce a tiny fireball of quark-gluon plasma, a direct window into the universe's first moments. But within that chaos, a subtle accident happened. A universe-saving accident. For reasons we still don't fully understand, the symmetry between matter and antimatter wasn't perfect. Out of every billion pairs of quarks and antiquarks that annihilated each other, one solitary quark was left behind. Just one. That minuscule imbalance, it's called baryogenesis. It's a mystery, and it's the only reason you're here to contemplate it. Without that 1 in a billion asymmetry, all matter and antimatter would have wiped each other out completely, leaving a cosmos of nothing but featureless light. Those leftover quarks, they were the survivors. They were the raw material. They would cool and bind, becoming the foundation for everything solid in the cosmos. The quark soup couldn't last. The universe kept stretching, and as it expanded, it cooled relentlessly, and when the temperature fell below 1 trillion degrees, something fundamental changed. The quarks, these free, independent particles, they suddenly lost their freedom. This happened around 1 microsecond after the beginning, 1 microsecond. In that instant, the energy of the cosmos dropped below a critical point, and the strong nuclear force, one of the fundamental forces, it finally gained the upper hand. Its grip became absolute, and it did what it was meant to do. It confined the quarks. They couldn't zip around independently anymore. They were pulled together, bound permanently by gluons into new composite particles. Hadrons, this is hadronization. You can think of it like a phase change, like steam cooling enough to condense into liquid water. The free quarks and gluons condensed into the first stable pieces of matter. And the most important hadrons were protons and neutrons, the cores of every future atom frozen into existence, but this birth came with a great annihilation. Remember those leftover quarks from the 1 in a billion accident? They had their opposites, antiquarks, and as hadrons formed, matter and antimatter met. A final, furious confrontation. Protons met antiprotons, neutrons met antineutrons. They collided and obliterated each other, flashes of gamma radiation. A storm of light, erasing nearly everything, but nearly is the key word because of that tiny, primordial asymmetry, that slight favor for matter, a remnant survived. When the annihilation storm faded, for every billion particles destroyed, one single proton or neutron was left floating in the aftermath. That's all the solid matter in our universe. Every star, every planet, every person. We are made from that 1 part in a billion surplus. Everything else was converted into raw light, light that still fills the cosmos. And so the universe entered a new phase, no longer a plasma of free particles. Now it was a hot, thick fog, a soup of atomic nuclei, mostly hydrogen and helium nuclei, which are just single protons or pairs of protons and neutrons swimming in a sea of free electrons and blinding light. Photons couldn't travel far. They'd bounce off an electron, then off a nucleus trapped in a constant scramble. The cosmos was opaque, a glowing, impenetrable mist. And it would stay that way, hot and dense and blind, for a very, very long time. The stage was set, but the lights for now were still on, far too bright to see anything at all. That blinding fog wasn't the only thing. There was another kind of particle, a more elusive one. This was the Lepton epoch. Leptons are the lightweight family. The electron is the most famous, but back then, space was full of them, electrons and positrons. They were created in collisions, and they met and annihilated. Flashes of light, and there were neutrinos, trillions of them. Neutrinos are ghostly, they're tiny, neutral. They barely notice the rest of the universe. They only feel the weak force and gravity. They ignore almost everything else. For a while, even they were trapped. In that hot, dense soup, they bounced around. Part of the mix, but the expansion kept going. The temperature dropped. And then, about 1 second in, something happened. The universe cooled enough. Neutrinos couldn't find partners anymore. The density dropped. The weak forces short reach, they were suddenly alone. They stopped colliding, they decoupled. And they streamed out into the expanding darkness, never to be disturbed again. That left an imprint, the cosmic neutrino background, a sea of these ancient particles. Still flowing through everything, trillions pass through you every second, silent relics from the first second. It's a fossil, even older than the cosmic microwave background, waiting for us to detect it. Then, after that, another annihilation ended. The electron and positron creation couldn't keep up. Matter and antimatter met one last time. Almost every electron found a positron. They vanished into energy, but like with the quarks, that tiny asymmetry meant something, a 1 in a billion surplus. A few electrons remained, just enough to one day balance the protons and the energy from that final annihilation. It didn't make new particles, it went back into the light. It reheated the photon bath, so that blinding fog of radiation, it would stay dominant for eons. The universe was clarified then, but still opaque. Atomic nuclei drifted in a searing light. And for the next 380,000 years, nothing changed, nothing except the slow cooling of everything. 380,000 years is a long time. The universe could wait, but at the start, for the first 3 minutes, it wasn't patient at all. The temperature had dropped from trillions of degrees down to 1 billion. 1 billion is still incredibly hot, but it was cool enough for a new bond to form, not between quarks, between atomic nuclei. This was the window, Big Bang nucleosynthesis. For about 17 minutes, the whole cosmos was a fusion reactor, an unimaginably vast one. The protons and neutrons left over from before, survivors of the annihilation, were finally moving slow enough. When they collided, the strong force could capture them, fuse them. A single proton, a hydrogen nucleus, would capture a neutron, become deuterium. Then these deuterium nuclei would collide. Fuse again, form helium, helium-4, 2 protons, 2 neutrons. It was a frantic dance, and the universe was expanding so fast, the window was brutally short. It slammed shut after maybe 20 minutes. By then the density was too low, the temperature too low, no more nuclear reactions. The work was done, the ledger was written. When the fusion fires died, the elemental budget was set. By mass, about 75% hydrogen nuclei, nearly 25% helium-4. And a tiny fraction, less than 1%, was everything else. Trace amounts, deuterium, helium-3, lithium-7. That was it. All the other elements, the carbon in your cells, the oxygen you breathe, the iron in your blood, none of that existed yet. That would wait for stars billions of years in the future. For now, the universe was simple. A soup of bare atomic nuclei and free electrons, still bathed in that searing light. And this prediction, we can test it. We look at the oldest clouds of gas far from any stars. We measure their composition, the amounts of hydrogen, helium, deuterium, lithium. They match the predictions with stunning precision. It's a triumph of cosmology, a receipt from the first 3 minutes preserved, so these nuclei were forged. The raw ingredients, but they were still naked, charged, trapped. The next great change would need even more patience, a much deeper cooling, 380,000 years. That's how long the universe waited. It was still this searing plasma, completely opaque, cooling moment by moment. Those bare atomic nuclei, mostly hydrogen and helium, they drifted in a sea of free electrons. And the light, the photons from the Big Bang's afterglow, they were trapped. A constant, frenzied dance. It's like being inside a cloud so thick and bright that light can't travel more than a tiny distance before it bounces off an electron. That's what it was, a glowing, uniform fog. If you could be there, your entire world would be featureless, a brilliant white, no stars, no galaxies, no points of light anywhere. Just a hot, dense mist, expanding and slowly cooling. This was the cosmic dark ages, a misnomer because it wasn't dark. It was blinding, but dark in the sense we understand. There were no sources, no objects, nothing to see but the fog itself. And during this immense stretch of time, the most important work was happening in near silence. Gravity, the weakest of the forces but with infinite reach, it was finally getting its chance. Those microscopic quantum ripples from inflation, now stretched to cosmic size, they were the blueprint. Tiny variations in density, places where, by the merest fraction, there was a little more hydrogen gas than the area next to it, and gravity is patient. It's relentless. It pulled ever so slightly on those overdense regions. More gas would drift toward them. Their gravity would grow a tiny bit stronger. A feedback loop of astonishing slowness. Over hundreds of thousands of years, these regions grew, from imperceptible whispers into faint smudges in the distribution of matter. The first potential homes for everything to come. All the while, the universe kept expanding, and as it expanded, it cooled. The particles lost energy. They moved more slowly, and this cooling set the stage for the single most important event since the Big Bang itself. A change so fundamental it would make the universe visible for the very first time. The temperature was dropping toward a critical threshold, a few thousand degrees, cool enough for a charged particle to finally, after all this time, find a partner and settle down. The temperature dropped below 3,000 degrees. After 380,000 years, the universe had expanded enough to cool, and the particles, they'd been moving too fast to connect, but now they slowed. An electron with its negative charge could be pulled in by a hydrogen nucleus, a single proton. They came together, forming the first stable hydrogen atom. Neutral, the same thing happened with helium. That event is called recombination, though it was really the first combination, and the universe lost its free electrons. That changed everything. It was like a dense fog, so thick you can't see through it. Then, instantly, the fog clears. The air becomes transparent. You can see for miles. That's what happened. The photons of light had been bouncing off electrons constantly, but now they were set free. They had one last collision with a particle, and then they streamed out. Into the clear universe unimpeded. For the first time, light could travel in straight lines. The universe became transparent. That moment, that last scattering, is frozen. Those photons have been traveling ever since, for 13.8 billion years, but the universe kept expanding, and as space stretches, it stretches the light moving through it. The wavelength gets pulled longer, from visible light to infrared to microwaves. That ancient flash released when atoms formed is what we detect now as a faint, cold whisper. The cosmic microwave background, it fills every bit of space. It's the oldest thing we can see, a snapshot of the infant cosmos from when it was just a fraction of its current age. Its discovery was almost an accident. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were trying to fix a persistent hiss in their antenna at Bell Labs. They cleaned out pigeon nests, checked every connection. The noise wouldn't go away. It came from every direction all the time. They had found the echo of creation itself. That nearly uniform glow, just a few degrees above absolute zero, confirmed the Big Bang theory, but it's not perfectly uniform. When we map the CMB with precision, we see tiny variations. Flecks of slightly warmer and cooler spots, differences of just 1 part in 100,000. These aren't flaws. They're the fossil imprints of those primordial quantum ripples from inflation. The seeds, the slightly denser regions which show as slightly cooler spots, had a little more gravitational pull. They were the starting points, the blueprints, from which gravity would sculpt every galaxy, every cluster, the whole cosmic web. So a map of the cosmic microwave background is like looking at the genetic code of the entire observable universe. The end of that plasma fog marked the start of the cosmic dark ages, because now, with neutral atoms and a transparent universe, there were no more sources of light. The primordial glow had redshifted away. The first stars were still hundreds of millions of years off. The cosmos entered a long, quiet night, a vast, dark sea of simple gas waiting for the first spark to ignite. The first true darkness came after that light faded. For almost 100 million years, the cosmos was silent. No stars, no galaxies, just a black, expanding void. A cold sea of hydrogen and helium gas drifting, but it wasn't still. Gravity was still at work. It had been working since the beginning, and now it was pulling on those faint blueprints, the ones left in the cosmic background. It pulled more and more gas into the denser spots. These weren't just clouds of normal matter. They were anchored by something else, dark matter. This invisible stuff, it feels gravity but not light. It had already settled into huge, faint halos. They were the skeletons, and into these dark matter scaffolds, the neutral gas began to flow, gathering. Cooling, condensing into the first protogalactic clouds. For eons, they just swirled in the dark, getting denser at their cores. The pressure built, the heat built. And then, in the deepest pockets of these nurseries, a line was crossed. Gravity finally won. It beat the outward push, and a cloud's core collapsed. In that inward rush, hydrogen atoms were squeezed together with unbelievable force. Nuclear fusion ignited, and the universe saw a new light, for the first time since the afterglow faded. The first star was born. These weren't like stars today. Astronomers call them population 3 stars, the first generation. They were monsters, made of nothing but that pure, primordial hydrogen and helium. No heavier elements to help them cool, so they grew. They grew huge, hundreds of times more massive than our sun, maybe even 1,000 times, a star so big our whole solar system could fit inside. Their brilliance was terrifying. They burned at ferocious temperatures, a fierce blue-white light, millions of times brighter than the sun, but that power has a cost. A star that massive lives fast, it dies young. Its nuclear furnace burns through its fuel in just a few million years, a blink, and its death was as spectacular as its birth. When its core ran out of fuel, it couldn't hold up its own weight anymore. It collapsed, then rebounded in a titanic explosion, a supernova of staggering power. And in that final blast, something miraculous happened. The heat and pressure forged new atomic nuclei, elements that had never existed: carbon, oxygen, silicon, iron. For the first time, the universe wasn't just hydrogen and helium. The furnaces of those first stars had cooked the raw ingredients into something more. And in their violent deaths, they scattered these new elements out into the gas clouds. This was cosmic pollution, the first enrichment. It changed everything. The pristine gas was now seeded slightly with the ash of dead stars. This dust would become the building material for the next stars and for the planets that might orbit them. The chemistry of the cosmos had begun. The dark ages were over. A new dawn was breaking, a dawn filled with starlight. That new dawn was violent. The universe had gone dark and quiet after the first light faded. But now it was awake, and it was angry. Those first stars weren't just shining, they were screaming. Their light wasn't gentle, it was a torrent. High-energy ultraviolet radiation pouring out into the dark. And that radiation did something. It began to tear the universe apart, atom by atom. For the neutral hydrogen gas, that peaceful sea filling all of space, this was an apocalypse. A single photon of that fierce light, carrying immense energy, would slam into a hydrogen atom. It would strike the electron, blast it free from its orbit around the proton. The atom was ionized again, split back into its charged pieces. This process on a cosmic scale is called reionization, the second great ionization of the universe. The first one ended when atoms formed and the cosmic microwave background was released. Now, hundreds of millions of years later, the universe was being reionized. Not by heat, by starlight. This wasn't quick. It unfolded over hundreds of millions of years, starting around 150 million years after the Big Bang, probably finishing by the 1 billion year mark. Think of it like a fog lifting, but not all at once. The first stars and galaxies ignited in isolated pockets. Around each one, a bubble of ionized gas would form, a bubble of clarity in the neutral fog. As more stars were born, and as the first supermassive black holes began to power quasars, these bubbles grew. They began to overlap, they merged, until eventually the bubbles filled all the space between galaxies. The intergalactic medium became a plasma again. Not hot and dense like the primordial soup, but thin and ionized, a ghostly sea of charged particles that cleared the final fog. Light from all the newborn galaxies could now travel across the cosmos. Largely unimpeded, the dark ages were finally over. How do we know this happened? We look for the shadows. Astronomers point telescopes at the most distant quasars. beacons of light from near the edge of the observable universe. As that light travels to us, it passes through billions of light years of intergalactic gas. And in the spectra of that light, they see dark bands, specific gaps where light has been absorbed. These are the fingerprints of the last patches of neutral hydrogen, the final vestiges of the fog that hadn't yet been burned away by the advancing wave of reionization. By mapping these absorption lines at different distances, astronomers can chart the progress of this great clearing. It's like finding burn marks on a page to understand how a fire spread. Reionization was the universe's coming of age. It transformed the cosmos from a collection of isolated, flickering lights in a dense fog into an interconnected, transparent arena, a stage set for the grand, star-filled vista we see today, a stage where light and eventually our own gaze could travel freely. The universe had cleared its throat, the great reionization swept away the final fog, and the stage was set for a new kind of construction, a frenzy of building on a scale we can barely comprehend. This was the epoch of galaxy assembly, a golden age of cosmic architecture. From about 1 billion to 3 billion years after the Big Bang, the universe shifted. It stopped making just isolated, monstrous stars. It started forging entire cities of stars. Those first protogalactic clouds were the raw material. They were anchored by their dark matter halos. Gravity is a patient sculptor, but now it had help. The first supernova had enriched the gas. They added heavier elements. That was crucial. That cosmic dust acted like a coolant. It let giant gas clouds fragment more easily. They broke into smaller, denser clumps. So instead of forming a few behemoth stars, a cloud could now spawn millions of smaller ones. More stable suns, star formation rates skyrocketed. These weren't just collections of stars anymore. They were becoming coherent structures, islands in the void. The first true galaxies, and they were hungry. They grew by merging. Smaller galaxies, drawn together by gravity, would spiral toward each other over hundreds of millions of years. They'd collide, not with destructive crashes, but with a slow-motion dance. Their stars are so far apart, they'd mostly pass right by, unharmed, but their vast clouds of gas would slam together. They'd compress, and that would trigger explosive new waves of star birth. We see the evidence of this everywhere, in the twisted, distorted shapes of distant galaxies. The Hubble and James Webb Space Telescopes capture them. Those deep-field images are time machines. They show us this era directly, galaxies that look like train wrecks. Tidal tails of stars streaming into space, brilliant blue knots marking bursts of newborn stars. It was a chaotic period, a creative period, and at the heart of many of these growing galaxies, something else was stirring. A darkness was gathering. Gas got funneled to the very center by the mergers. That gas fed the birth and growth of supermassive black holes, entities with masses millions or billions of times our sun. They became engines. When they fed, they didn't just swallow matter. They lit up as quasars, the most luminous objects in the universe, beacons that could outshine their entire host galaxy. Their fierce radiation, their powerful jets, they helped shape the galaxy around them. They regulated star formation. They blew gas out into intergalactic space. Over time, through countless mergers and cycles of birth and feedback, galaxies settled into the familiar forms we know, the elegant, star-forming spirals. The round, quiescent ellipticals, those were likely born from major collisions, but no galaxy is an island. Gravity was weaving them together into a larger tapestry. They began to cluster along faint lines, along intersections, forming groups, then clusters, then superclusters, and between these great walls and filaments of light, something else became apparent. Vast, empty regions, cosmic voids, hundreds of millions of light years across, containing almost no galaxies at all. This is the cosmic web, the large-scale structure of the universe. A sponge-like architecture of matter with great empty bubbles in between. It's the final imprint, the magnificent imprint of those quantum seeds from inflation. Grown to cosmic proportions by gravity over billions of years, the universe was no longer a simple place. It had become a bustling metropolis, an architecturally rich landscape of stellar cities. Connected by dark highways, illuminated by the glow of countless suns, inside those stellar cities, something was quietly changing. It was the life and death of stars that built our world. The first generation, those massive giants, lit the darkness and made the first heavy elements, but they were a flash. The universe needed stable furnaces for the finer work. Stars like our Sun, they formed from gas clouds already seeded with stardust, the ash from those earlier titans. That dust was the secret. It let the clouds break into smaller clumps. A star like ours could take shape, settling into a balance for billions of years. At its core, a nuclear fusion reactor ignited, squeezing hydrogen into helium, releasing the energy that makes stars shine. But the core, over time, becomes a crucible. As the hydrogen runs low, the star adjusts. For a star like the Sun, the core contracts and heats. It gets hot enough to fuse helium into carbon and oxygen. That's stellar alchemy. The star isn't just a light source anymore. It's a factory forging the elements of complexity. But there's a limit. In stars like ours, fusion stops at carbon and oxygen. The core isn't hot or dense enough to go further. The truly heavy elements like silicon and iron need a more violent end that comes from much bigger stars. In their hearts, fusion happens in layers like an onion. Hydrogen fuses in an outer shell, helium deeper in, and at the very center, under immense pressure, silicon fuses into iron. And iron is a dead end. Fusing iron doesn't release energy, it consumes it. So when an iron core grows too large, the star's support vanishes. In less than a second, the core collapses. Then it rebounds in a cataclysmic explosion, a supernova. The shockwave blasts the star's outer layers into space, and in that brief inferno, elements heavier than iron are forged. Gold, silver, uranium. All the elements are created in these explosions or in neutron star mergers. The star dies, but in its death, it scatters a cloud of new atoms across light years. This enriched gas, this cosmic recycling bin, is where planets are born. In quiet corners of galaxies, a cloud of this dust and gas begins to collapse under gravity. It forms a spinning disk around a newborn star. Within that disk, microscopic dust grains of silicon and carbon begin to stick together. They form pebbles, then rocks, then planetesimals. In a gentle dance of collisions, these clumps grow. Closer to the star, where it's too hot for ice, rocky planets like Earth take shape. Farther out, where it's cold, ice joins the rock, building the cores of gas giants like Jupiter. Asteroids and comets are the leftover material, the scraps from the workshop. Every atom in your body, except the hydrogen, was forged in a star that died before our sun was born. The oxygen you breathe, the carbon in your DNA, the iron in your blood, all of it was once stardust scattered by a supernova. Our solar system and billions like it are the result of this cycle. Stars live, create, die, and recycle. Over billions of years, this turned a universe of simple hydrogen into one rich with the chemistry for rocky worlds and oceans. It set the stage for the next possibility, that on some of those rocky worlds under a stable star, the chemistry might become complex enough to wake up and look back at the stars. That creative frenzy had a climax. There was a golden hour for the cosmos. Astronomers call it cosmic noon. This was about 3 to 4 billion years after the Big Bang, when the universe was maybe half its current age. Everything reached a peak. The rate of star formation hit its maximum. The universe was at its most productive, its most luminous. If you could have looked across the cosmos then, the view would have been dazzling. Galaxies weren't the settled, orderly spirals we often see now. They were gas-rich and turbulent. They collided and merged with a stunning frequency. And every major collision was a festival of creation. When two giant gas clouds slammed together, the shockwaves compressed the material that ignited firestorms of new stars. These weren't just a few stars here and there. These were starburst galaxies. They were birthing hundreds, even thousands of solar masses worth of stars every single year. For comparison, our own Milky Way now makes maybe 1 or 2 suns per year. Back then, entire galaxies shone with a fierce blue-white light. That's the signature of countless hot, young, massive stars. The universe was a fireworks display on the grandest possible scale, and at the heart of many of these brilliant galaxies, the central black holes were feasting. As gas funneled inward from the chaotic mergers, these supermassive entities gorged themselves, but they didn't just swallow matter silently. As material spiraled into the accretion disk, it heated to millions of degrees. It blazed with radiation. They became quasars, beacons so powerful they could outshine every star in their host galaxy combined. Their intense light and powerful jets poured energy back into their surroundings. They shaped the very galaxies they lived in. This was a universe of extreme contrasts, immense creative energy driven by gravity's relentless pull, and equally immense destructive power concentrated in those dark hearts. It was a vibrant, energetic, almost violent adolescence. Cosmic noon represents the zenith, the high water mark of the universe's creative output. After this period, the fuel began to run low. The mergers became less frequent as the universe expanded, pulling galaxies farther apart. The great reservoirs of cool gas within galaxies were either turned into stars or blown away. Blown away by supernova and quasar winds, the overall pace of star formation began a long, gradual, and irreversible decline. The universe, having reached its brilliant peak, began its slow journey toward a quieter, more settled future. The fireworks were winding down. They left behind the glowing embers of mature galaxies and a legacy of elements that would one day form planets like our own. That cosmic noon, that brilliant peak, couldn't last. The universe had been expanding for its first several billion years, but that expansion was slowing down. All the matter, all the galaxies, all the dark matter, it was all pulling on everything else, a cosmic tug of war, and gravity was winning, putting the brakes on the stretch of space itself. The future seemed set for a gradual slowdown, but the cosmos had a surprise. There was a hidden player waiting. Around 5 to 7 billion years after the Big Bang, something changed. The slowdown stopped, and then, against all intuition, the expansion started to speed up. Space itself began stretching faster and faster. So what could overpower the collective gravity of everything? The answer for now is just a name: dark energy. It's not a substance like dark matter. It's not made of particles. It seems to be a property of space itself. A kind of latent energy woven into the vacuum, and it has a repulsive effect. Where gravity pulls, dark energy pushes. For billions of years, the universe was dense enough that gravity's pull was stronger. But as space expanded and matter thinned out, the balance tipped. The repulsive effect of dark energy, which grows as space grows, finally became dominant. Like a long-distance runner finding a second wind, but this wind never fades, it only gets stronger. We discovered this by looking into the deep past. In the late 90s, 2 teams of astronomers were studying a specific kind of stellar explosion, a Type 1, a supernova. These are cosmic standard candles. They always explode with roughly the same brightness, so by measuring how dim they appear from Earth, you can calculate their distance very accurately. And by looking at the redshift of their light, you can see how much the universe has stretched since the explosion. The teams, led by Saul Perlmutter and by Brian Schmidt and Adam Rees, they expected to confirm the universe was slowing down. Instead, they found that distant supernovae were fainter than they should have been. They were farther away. The only explanation was that the expansion had been slower in the past than it is now. It was accelerating. The discovery was so shocking, the teams triple-checked their data for years before announcing it. It earned them the Nobel Prize in Physics in 2011. That was the moment cosmology turned on its head. We learned that about 70% of the universe's total energy is this mysterious dark energy. Ordinary matter, the stuff of stars and planets and us, is less than 5%. Dark matter makes up about 25%. We are the cosmic afterthought. The nature of dark energy is the biggest mystery in modern physics. The simplest idea is that it's Einstein's cosmological constant, a fixed energy density of empty space. But its measured value is extraordinarily tiny, yet not zero, which puzzles theorists. Could it be a dynamic field that changes over time, like the inflatoned field that drove the early universe's inflation? We call those ideas quintessence. Or is it a sign that our theory of gravity, Einstein's general relativity, breaks down on the largest scales? We simply do not know. What we do know is that this transition marked a fundamental shift in the universe's destiny. The baton passed from gravity to dark energy. The fate of the cosmos is no longer to coast or collapse under its own weight. It is to fly apart faster and faster into a future shaped by this silent, repulsive force. The long-term story of everything was rewritten in that moment, billions of years ago, by something we cannot see and do not understand. 13.8 billion years, that's how long it's been. We're here now, in this moment, a snapshot. Our galaxy, the Milky Way, it's a spiral, a mature one. It got this big by pulling in smaller galaxies over all that time. Its arms still have those pink clouds where stars are born, but that frantic period, that's over. The black hole at the center, it's quiet now. It's not that bright quasar it might have been. Our sun is middle-aged, a yellow dwarf. It formed 4.6 billion years ago from a cloud. And that cloud was made from older stars, stars that died and left behind the stuff for planets, for life. On the third planet from that sun, something happened. Chemistry turned into biology. Life came out of that. It evolved, it got complex, and then it became aware. The universe could look at itself, it could wonder. It could ask where it came from. So this is our moment. We're at a pivot point. We can look back. Our telescopes show us galaxies from billions of years ago. We can piece together the story from the beginning to our own solar system, and we can look forward, too, using physics to see where it's all going. Right now, the universe is in a kind of balance. Dark energy is in charge. It's making space expand faster, pushing galaxies apart. But gravity still has its hold on smaller scales. It holds our galaxy together. Our local group, the Milky Way, Andromeda, the smaller ones, they're in a slow dance. They'll merge, but not for billions of years. Stars are still being born. But it's a trickle, nothing like that huge burst earlier on. The fuel for those star factories, it's running low. The universe is getting quieter, more settled. This is the late afternoon of the star era. The light is still here. The sky is still full of things to see, but that bright, chaotic noon is gone. This is where we are. A brief window. The cosmos is old enough to know itself and still young enough to have mysteries left. In all that slowly darkening space, that window of light is closing. The great stellar factories are running out of fuel. The raw material, the hydrogen and helium, it's being locked away. Some gets fused into heavier elements inside stars. A lot of it gets blown out into the vast spaces between galaxies by supernova and by the winds from supermassive black holes. And with dark energy accelerating the expansion, the gas that's left behind inside galaxies and between them, it just gets more diffused. More spread out over tens, hundreds of billions of years. This process finishes. Star formation won't end with a bang. It'll be a long, slow sigh. The rate, which is already a fraction of what it was, it'll plummet toward zero. The last new star will ignite in some forgotten dwarf galaxy, and after that, the universe lives on the light of the stars it already has. Those won't be the brilliant blue giants. Those massive stars, they live fast, die young, they're already gone. The main sources of light then will be the slow-burning candles, red dwarfs, stars like Proxima Centauri. They're small, cool, incredibly frugal with their fuel. A typical red dwarf can shine for trillions of years. They'll outlive every other type of star by a huge margin. In that era, the night sky on any surviving planet would have this dull, crimson glow. Our constellations, they'd be long gone. Their stars burned out, collapsed into dark remnants. And the cosmos itself, its architecture, it's still changing, but on a slower, grander scale. Gravity's local pull still wins over dark energy's push inside bound clusters. The great dance of galaxies continues. The Milky Way and Andromeda, they're on a collision course. They'll merge in 4-5 billion years, form a single giant elliptical galaxy, Milkomda. That'll happen elsewhere too. Over hundreds of billions of years, all the galaxies in a cluster coalesce into these smooth, elliptical behemoths. They're just collections of ancient stars orbiting in a chaotic swarm. No spiral arms, no fresh gas for new stars, so the universe doesn't go dark all at once, but it grows steadily dimmer. The brightest beacons, the blue supergiants, the white-hot quasars, they're already relics. As the remaining larger stars like our Sun, exhaust their fuel and fade, the overall luminosity of the cosmos drops. This is the beginning of the end for the stelliferous era. That's the age we live in now, the age of stars. It's a chapter that's lasted billions of years, but it's not permanent. We're in its vibrant, mature phase. And we can see the long twilight that's coming, the transition to a lonelier, darker phase. It's already written into the laws of physics. It's a slow fade. From a brilliant painting to a sketch in faint, red ink. What happens when the last red dwarf finally winks out? That's a story for an even more distant future. The last red dwarf goes dark. The universe has been dark for a very long time, but now it moves into its longest phase, the Degenerate era. That name, it's not about moral decay. It's a physics term, degenerate matter. It's what's left when gravity crushes normal atomic structure out of existence. The age of starlight is a distant memory. Now the cosmos is a graveyard, stellar corpses, and the only light comes from their leftover warmth. Three kinds of objects define this age. First, white dwarfs. They're the dense, Earth-sized cores of stars like our Sun, left behind after the outer layers drift off. They're not hot from fusion anymore. They just glow from residual heat, like an ember in a cold fireplace. They're held up against their own gravity by a quantum pressure electron degeneracy pressure. It's a final stand against total collapse. Over timescales we can't really imagine, these white dwarfs will cool. They'll dim from white to yellow to red and finally to black. They become cold, dark spheres of crystallized carbon and oxygen. Black dwarfs. The universe isn't old enough yet for even one to have formed. Second, neutron stars, the collapsed cores of bigger stars. They're city-sized balls of almost pure neutrons, incredibly dense. A teaspoon of that material would weigh billions of tons. They also glow with leftover heat, and they spin with powerful magnetic fields. But even their fierce energy bleeds away into space over eons. And third, black holes. The final endpoints for the most massive stellar cores. They give off no light of their own. You'd only know they're there by their gravity, silent, terrible gravity. This era is defined by a deep silence, broken by incredibly rare events. In the vast dark, two failed stars, brown dwarfs, might, after trillions of years, slowly spiral together and collide. That impact could briefly ignite fusion, creating a transient final star that shines for maybe a century in a sea of darkness, a fleeting flash, a last echo of the age of stars. Similarly, two white dwarfs in a slow dance might eventually merge. If their combined mass crosses a critical line, they could detonate in a final, lonely supernova. A last firework in an empty sky. Any planets that survived their star's death are frozen worlds now, adrift in the dark. Their surfaces are near absolute zero. Their atmospheres froze long ago, fallen as snow. Their silent tombs orbiting dead suns. The galaxy itself has changed through gravitational interactions over these immense eons. Stars, or their remnants, have been flung out into the void. The galaxy's structure evaporates. What's left is a diffuse, spherical cloud of these dark objects, slowly orbiting the supermassive black hole at the center. The elegant spiral is gone. All that's left is a ghost, a swarm of degenerate matter in the endless night. The dominant force isn't creation anymore. It's the slow, inexorable leak of heat into an expanding, ever colder universe. This is the degenerate era. A chapter that will last for a duration we can write down but can't really feel 100 trillion years. A span so vast it makes the entire age of stars seem like a brief spark, and even this is not the end. Even dead stars won't last. The degenerate era, that time of cold remnants, it's just a prelude. Way out in the future, times so long we can't really picture them. Even the most stable things start to fail. The universe moves into its most exotic chapter, the era of black holes. All those white dwarfs and neutron stars, they could end through something called proton decay. If protons aren't perfectly stable, and some theories say they aren't, then every atomic nucleus in every dead star will just fall apart over eons. The matter dissolves into lighter particles and energy, a slow, quiet disintegration. Maybe 10 to the 34 years or more. A single proton, the heart of a hydrogen atom, it might just cease to be. If that happens, those stellar corpses from the last era, they fade away. What's left is just their gravity black holes as the last large structures. Black holes become the only architects, the final monuments. Stellar mass black holes from dead stars, they drift in the dark. And in the centers of what were galaxies, the supermassive black holes, now unimaginably large from eons of mergers, they just sit there. Silent, they're not feeding anymore, nothing left to feed on. They're just pure gravity, but even they aren't permanent. Stephen Hawking had this insight: they have a faint temperature. At the quantum level, right at the event horizon, particle pairs can pop into existence. Usually they annihilate right away. But if one falls in and the other escapes, the black hole loses a tiny bit of mass. That's Hawking radiation. It's an excruciatingly slow leak. For a black hole the mass of our Sun, it would take about 10 to the 67 years, a 1 with 67 zeros. That number is so vast, it dwarfs the current age of the universe by more than 50 orders of magnitude. As the black hole loses mass, its temperature goes up. The evaporation speeds up, and in its final moments it's thought to vanish in a sudden burst of gamma rays, a last whisper. The stellar mass black holes go first. Then, over timescales that are basically eternal, even the supermassive giants at the galactic centers will shrink and evaporate. Their end might take 10 to the 100 years. Picture it: the largest, most powerful objects, rulers of galaxies for eons, shrinking down to the size of a mountain, then a boulder, then a grain of sand, before popping out of existence in a final flash. It's the ultimate dissolution of structure. What's left is a universe that's almost featureless, a thin, cold sea of fundamental particles, photons, neutrinos, electrons, positrons, and whatever comes from proton decay. All of it being pulled farther apart by the expansion, by dark energy. The radiation from all those final evaporations redshifts away, no more clumps of matter. No more sources of light or heat, no places where gravity makes a noticeable curve. The cosmos becomes profoundly simple and profoundly dark, a sea of near nothingness, getting colder and more dilute with every eon. It's the quietest state you can imagine, the universe having spent all its complexity, all its structure, all its stories, but even this isn't the final state. That final flash from a black hole is the last event, and then the universe enters its longest chapter, the dark era, sometimes called the photon epoch. All the great structures are gone. The stars, the planets, the black holes, they've all evaporated. What's left is a kind of soup, but it's the thinnest soup you can imagine. Just a few fundamental particles, separated by distances so vast they might as well be alone. Photons, the particles of light, but their light is stretched now into wavelengths longer than the observable universe. They carry no information, no warmth, just a faint, cold whisper. Neutrinos, those ghostly particles from the first second. They're still streaming through the void, electrons and positrons drifting. If protons are unstable, like some theories say, then even the memory of atoms is gone. Every atomic nucleus from the age of stars has disintegrated. There's no solid matter left, nothing to build with, nothing to see. The temperature of the entire cosmos is approaching absolute zero. Minus 273.15 degrees Celsius, the point where all molecular motion stops. It's not just cold, it's the deepest cold possible. The universe in this era is almost perfectly uniform, a near-empty void, no hills, no valleys, no concentrations of anything. Dark energy has done its work, stretching space so efficiently that every particle is isolated. Events become so rare they're essentially non-existent. Two particles might drift toward each other over a timescale longer than all the previous eras combined. Their meeting would be a cosmic accident, unimaginably rare. For all practical purposes, nothing happens. And this raises a question about time. We measure time by change, by events, the tick of a clock, the orbit of a planet, the decay of an atom. But here, in the dark era, change is imperceptible. The state of the universe is the same from one eon to the next. If there's no change, does the concept of time still have meaning? It becomes a coordinate without a heartbeat, a framework with nothing to frame. This is the universe in its ultimate simplicity. It has returned to a state of near featurelessness, but not like the beginning. That primordial singularity was hot and dense beyond comprehension. This is its opposite, cold and dilute beyond comprehension. It's the final, quiet sigh. A cosmos that has played out every possible note and now rests in a silence so complete it echoes forever. So that's the final state, heat death. It's not an explosion. It's not a collapse, it's just the end of events, the quiet end. The laws of thermodynamics lead there. The second law says entropy always increases. Disorder always grows, and the universe is a closed system. So over all this time, it's been moving one way, from that hot, dense, ordered beginning toward maximum entropy, everything spread out perfectly even, all energy diffused, no hot spots, no cold spots, no pressure differences, no gradients left. And without a gradient, no work gets done. It's like a cup of coffee in a cold room. The heat flows out until they're the same temperature. The energy's still there, but it's useless. You can't run an engine. The universe in heat death is that room, a cosmic room, every point the same frigid temperature, a few degrees above absolute zero. No light, photons stretched into meaningless ripples, no matter-forming structures. What's left is isolated by distances so vast they're infinite, no change. No difference from one place to another, the most uniform state, the most silent, the most still. Current cosmology points to this, dark energy, accelerating expansion. Other endings seem less likely now, A big crunch where gravity pulls everything back. A big rip where dark energy tears atoms apart. Less likely, the universe seems set on this gentle fade. It's a profound end to the story. From a single point of infinite potential, the cosmos flared into existence, built galaxies, stars, planets, gave rise to life and consciousness. Only to spend all that creative energy, to dissipate all its differences, to reach a perfect balance, a lifeless balance, a story from a brilliant, structured beginning to a dark, uniform end. Increasing disorder across trillions of years, the final chapter isn't a period, it's an ellipsis, stretching into eternity, a silent, eternal now. That silent, cold eternity isn't the only story. The path to heat death assumes dark energy stays constant, but we don't know if it does, so cosmology has to consider other endings, different behaviors for this energy. One possibility is much more violent. It's called the Big Rip. Imagine if dark energy doesn't just push, it grows stronger over time, its repulsive force increases. Not because space expands, but in itself, the acceleration becomes a runaway force, unstoppable. First, it tears apart the cosmic web, galaxy clusters bound by gravity, ripped from each other. Then individual galaxies are shredded, the stars inside them pulled apart. As the force grows, it overcomes the gravity holding solar systems together. Planets flung from their dead suns, then the force grows stronger than electromagnetic bonds, the bonds holding matter together, a planet or a person torn apart at the molecular level. And finally, in the last instant, the force exceeds the strong nuclear force, the force binding atomic nuclei, every atom in the universe violently dissociated. Into fundamental particles, space itself expands faster than light can travel within it. The universe ends not with a whimper, but with a catastrophic tearing. The fabric of reality, all of this could happen in a finite time, maybe hundreds of billions of years from now. It's a reminder, the fate of everything hinges on the precise nature of dark energy. Something we still don't know. The opposite vision is equally dramatic, more poetic in a way. What if the expansion doesn't accelerate forever? What if one day it slows, stops, and reverses? This is the big crunch. In this model, the collective gravity of all matter and dark matter eventually wins over dark energy. The universe reaches a maximum size. Pauses, then begins to contract. Galaxies rush toward each other. Their light blue shifts. The sky grows hotter and brighter. As the collapse accelerates, galaxies merge in a frenzy. The temperature of the cosmic background radiation rises, first to match star surfaces, then far beyond. In the final moments, the entire observable universe compresses back into a state of unimaginable heat and density, mirroring the Big Bang. It could collapse all the way back to a singularity, but some theories suggest this might not be an end. It could be a transformation, a cosmic bounce. The intense energies of the crunch could trigger a new expansion, a new Big Bang. This leads to cyclical models. Oscillating universes, the cosmos goes through endless cycles: bang, expansion, crunch, rebirth. Each cycle could be similar or wildly different, physical constants resetting. It's a vision of cosmic reincarnation, where endings are also beginnings. Discussing these isn't just speculation. It highlights a truth about our current understanding. The ultimate fate of everything, the quiet fade, the violent rip, the cyclical rebirth, it depends entirely on the properties of dark energy, a component that makes up most of the universe's energy, yet remains almost completely mysterious. Is it truly constant, like Einstein's cosmological constant, or is it a dynamic field that changes, something physicists call quintessence? Our measurements aren't precise enough yet to rule out these dramatic alternatives. Every new telescope, every deep survey of distant supernova and galaxy clusters, they gather data to pin down the equation of state of dark energy. the relationship between its pressure and density. This research is a race against cosmic time. Not for our survival, but for the story we tell about existence. The final chapter of the universe is still being written, not in stars, but in the subtle physics of empty space. That silent, dark eternity has a foundation we can't see, and through this whole cosmic story, from the first gravitational whisper to the biggest galactic city, there's been an invisible architect. Dark matter, it's not just a detail, it's the framework. The visible universe was built on it. Think of the early universe after inflation. There were those tiny density ripples. But ordinary matter, protons, neutrons, electrons, the stuff of stars and planets, it was still coupled to intense radiation. That light created pressure. It pushed against gravity. It smoothed out any clumps trying to form, like trying to build a sandcastle in a strong wind. The visible stuff couldn't get a grip. But dark matter is different. It doesn't interact with light. It feels gravity, but it's blind to that pressure from the primordial glow. So while ordinary matter was being buffeted, dark matter could gather. Quietly, patiently, it started pooling in those overdense regions from the cosmic blueprint. It formed vast, faint halos, invisible gravitational wells. And once those wells were deep enough, they became anchors. When the universe cooled and became transparent, ordinary matter finally fell. Hydrogen and helium gas flowed into those waiting gravitational pits. It followed the contours sculpted by dark matter. That dark scaffolding is what allowed galaxies to form so quickly, so richly. Without it, the universe would be more diffused, more lonely. The intricate cosmic web we see, the great filaments and clusters, that's primarily a map of dark matter's distribution. The glowing galaxies are just bright lights strung along its invisible threads. We know it's there from the gravitational signature. Galaxies spin too fast for their visible mass. Galaxy clusters hold together. Massive clusters bend light from behind them, gravitational lensing, revealing the hidden mass warping space. All the evidence points to one fact. For every bit of normal matter, every star, every planet, every one of us, there's about 5 times more dark matter. It's the dominant form of matter, yet after decades we still don't know what it is. The leading idea is a new, undiscovered elementary particle, something massive that interacts only very weakly. Scientists built sensitive detectors deep underground, hoping to catch the rare bump. Others look for indirect signals from space. So far, it's elusive. This has led to a different proposal. Maybe dark matter isn't a thing at all. Maybe it's a sign that our understanding of gravity, Einstein's general relativity, needs modification on the largest scales. Modified Newtonian dynamics, MUND. It suggests gravity behaves differently when it's extremely weak, like in the outer reaches of galaxies. It's a compelling alternative. But it struggles to explain all the observations, the patterns in the cosmic microwave background, the behavior of colliding galaxy clusters, so the puzzle stands. Is the universe filled with an ocean of unknown particles, or are the laws of gravity themselves not quite right? Unlocking this isn't just academic. It's essential to the complete story of cosmic evolution, from the first instant to the final fade. The fate of all structure in the very longest term is tied to this unseen majority. It shaped our past, it will influence the distant future. We're here at this exact point in cosmic history. That's the anthropic principle. We could only exist in a universe that's old enough, but not too old. A universe that's had time to cook, to take that primordial hydrogen and helium from the Big Bang and forge it into something more that required the full life cycles of stars. They had to be born, fuse lighter elements into heavier ones in their cores, and then die in supernova, scattering those new atoms. That takes billions of years. If the universe were much younger, say, only a few 100 million years old, those heavy elements, the carbon and oxygen and iron we're made of, they wouldn't be abundant enough. We wouldn't be here to ask, but if the universe were much older, that's a different problem. The era of stable, long-lived stars like our Sun would be over. The stellar furnaces would have burned out. The cosmos would be entering its long, dark decline, dominated by dead stars and black holes. A universe trillions of years into its future probably couldn't support complex chemistry or the stable planet's life needs. So our place in time isn't random. It's a necessary condition. We're in the sweet spot. The universe is mature enough to have built the periodic table, but still vibrant enough to provide energy for life. This privileged moment goes beyond our chemistry. It defines what we can see. Look up at the night sky. We live in an era where we can observe both the infant universe and its accelerating fate. The cosmic microwave background, that fossil light from 380,000 years after the Big Bang, has redshifted into microwaves, but it hasn't faded away completely. It's still detectable. In another few tens of billions of years, as expansion continues, that afterglow will be so stretched and faint it might be invisible to any future observers. And the evidence for dark energy, the accelerating expansion we found by looking at distant supernovae, that's also a feature of this epoch. We're at a pivot point. Late enough that dark energy has become dominant and revealed itself, but early enough that galaxies are still visible, still close enough to study. So we find ourselves at a crossroads of observability. We can look back nearly to the beginning, and we can deduce the long, cold future. This is a fleeting window in the 13.8 billion-year story. A window that may be open only for a cosmic instant. It suggests our time here isn't just a biological accident. It's a chronological necessity. We are the universe, grown old enough and complex enough to look back upon itself, to trace its own timeline from a single point of light to the contemplation of an endless dark. We know this because the story of the universe is written in light. We read it with telescopes, and telescopes are time machines. You look at a galaxy 100 million light years away, and you're not seeing it now. You're seeing it as it was 100 million years ago. The light has been traveling that whole time, so we're like archaeologists digging back through layers of time. The deeper we look, the further back we go. The James Webb Space Telescope looks so deep it sees galaxies from just a few 100 million years after the Big Bang. That light is a fossil. It carries information from the universe's youth. Then there's the cosmic microwave background, that faint glow everywhere in space. It's a direct snapshot, a picture of the universe the moment it became transparent, when atoms first formed. Satellites like Planck mapped its tiny temperature variations. That map is a blueprint, the seeds for all the galaxies. It's a time capsule from 380,000 years after the beginning. The chemical makeup of the cosmos is another clue. In the oldest clouds of gas far from any stars, we find a specific mix, about 75% hydrogen, 25% helium, and tiny traces of deuterium and lithium. That mix matches with stunning accuracy what was predicted for the Big Bang's first few minutes, the nuclear reactions that could only happen in that hot, dense state. It's like a receipt from the universe's first 3 minutes. We use the laws of physics as a guide. We take those starting conditions, the ripple pattern from the background radiation, the known amounts of dark matter and dark energy, and we put them into supercomputers. We run simulations. We let virtual universes unfold for billions of years, and what comes out looks uncannily real. The great filaments of galaxies, the vast voids, the clusters. It all emerges from those simple beginnings, governed by gravity and expansion. That's a powerful confirmation. It tells us the basic story is right. Sometimes the biggest discoveries come from connecting theory to something unexpected. Dark energy is the perfect example. Astronomers studied a certain type of stellar explosion in distant galaxies. They used it to measure how the expansion rate has changed over time. They expected to find the universe slowing down, but they found it speeding up. That one shocking observation, confirmed over and over, forced us to rewrite the future. It showed the cosmos is dominated by a mysterious repulsive force we still don't understand. So that's how we build the timeline, not from one clue, but from many lines of evidence converging. It's a detective story. Each observation is a piece. The whisper of the background radiation, the death of a supernova, nuclear physics tells us about the first minutes. The behavior of light tells us about expansion. The distribution of galaxies tells us about dark matter. We cross-check these stories. When they all point to the same narrative, we gain confidence. The universe is a history book written in the language of physics, and we're just learning how to read it. Our timeline is a map, and the edges of that map say here be dragons. We've traced a story from a singularity to a cold, silent end. But at both extremes and in the cosmos we see now, our knowledge hits a limit. It dissolves into mystery. What happened at the exact moment of the Big Bang? Our equations break down there. To see that first instant, we need a theory of quantum gravity. We need to know how gravity works on the scale of atoms. We don't have that. There are competing ideas. String theory says everything is made of tiny vibrating strings. It says the Big Bang could have been a collision of higher dimensional membranes. Loop quantum gravity says space itself is woven from a fabric of tiny loops. That would prevent a true singularity. These are beautiful ideas. They're mathematically elegant. But they're untested. For now, they live in the realm of theory. They're waiting for an experiment, an observation, to bring them into the light. Then there are the hidden components. The things that shape the universe's fate. We call them dark matter and dark energy. Those names confess our ignorance. Dark matter is invisible scaffolding. We see its gravitational shadow holding galaxies together. We see it bending light, but after decades of searching, with detectors underground, with telescopes scanning the sky, we haven't caught a single particle of it. Maybe it's not a new form of matter. Maybe our laws of gravity are just wrong on cosmic scales. That debate continues. Dark energy is even more elusive. Is it a constant energy of empty space? Einstein suggested that once. Or is it a dynamic field? Could it change over eons? Could it even reverse, leading to a different fate? Our measurements aren't precise enough to say. These aren't small gaps, they're chasms, and they dominate the cosmic budget. This leads to the most speculative frontier. Is our universe unique? The theory of cosmic inflation suggests a staggering possibility. The multiverse. If the inflattened field decayed differently in different regions, each patch could inflate into its own separate universe. Each with its own physical constants, a vast, maybe infinite ensemble of cosmic domains. In some, gravity might be stronger, atoms might be unstable. In others, conditions might never allow a star to form. We happen to live in one where the numbers allow for galaxies and planets and life. This idea is compelling to theorists. But can we ever test it? If other universes are causally disconnected from ours, forever beyond our reach, does the idea move from science into philosophy? Even our vision of the far future, that long slide into heat death, is a colossal extrapolation. We're taking physics confirmed in labs and in our local cosmos. We're projecting it over timescales like 10 to the 100 years. Can we be sure the laws themselves are eternal? Could some unknown process emerge on those unimaginable scales? Could it rewrite the ending? We have to hold our conclusions with humility. The timeline we've traced is the best story we can tell with the evidence we have. It's a triumph of human curiosity and reason, but it's not the final word. It's a chapter in a book that's still being written. Every new telescope, every deeper observation, every theoretical breakthrough is poised to refine this biography. It might even revolutionize it. The universe's story isn't a relic, it's a living narrative, and we're in the middle of reading it. Our whole history, everything we've recorded, is just a blink. A moment. We're here in this quiet stretch between two silences, and it's easy to feel small, temporary, but that's only one side of it, because the timeline shows something else. The universe spent billions of years preparing, cooling down, building elements inside stars. All that work led to this window, a short time when the universe could become aware of itself. And that window is open now. We're not just watching, we are that process. The carbon in us, the calcium, it was made in stars that died before our sun existed. We are the universe grown complex enough to ask where it came from. So this moment isn't an accident, it's a flowering, a point of self-reflection which changes the question of meaning. If the long-term fate is dissolution, does that erase purpose now? Not really. It reframes it. A sunset isn't less beautiful because it ends. Its transience is part of it. In the same way, our time of light and life feels more poignant against the coming dark. Our struggles, our art, our love, they aren't erased, they become part of the story. A vivid chapter in the story of structure. So maybe legacy isn't about carving something permanent into an impermanent cosmos. It could be about the quality of awareness we foster in this privileged sliver of time. Understanding our place bridges a gap. It connects the science of particles and forces with our human need for context. We're pattern seekers who found the largest pattern. Knowing the full arc from a fiery start to a cold end doesn't give us a predetermined purpose. Instead, it sets a stage, a breathtaking stage, and it invites us to decide what matters inside our brief, brilliant moment of light. The universe created the conditions for questioning. Our response to that gift is ours to write. That drive to map the cosmos, it's a human legacy, a story of curiosity. It goes back to the first person who looked up at the night sky and just wondered. Those ancient sky watchers, they charted the cycles, the moon, the planets. They were taking the first steps, building a foundation, a language for the heavens. That slow accumulation of knowledge passed down, it eventually gave us the tools. Tools to ask bigger questions, not just how the planets move, but where they came from. Not just what stars are, but what they mean, for the beginning of everything. This quest transformed over millennia. It moved from mythology to mathematics, from philosophy to physics. It required inventions, the telescope, the spectroscope. The satellite, it demanded minds like Newton, who gave us gravity, and Einstein, who reshaped space and time. It called for patient work, countless researchers. Analyzing Starlight, building detectors, writing code for simulations. This timeline we've traced, it isn't just a list of events, it's a cultural achievement. A collaborative masterpiece of human reason. It belongs to no single nation, no single people. It's a shared understanding, built by a global community looking outward together. In a world often divided, this cosmic perspective offers a frame, a unifying one. We are all made of the same stardust, riding the same expanding fragment of space-time. Toward the same distant future, knowing this story changes us. It turns us from inhabitants of a planet into witnesses, conscious witnesses to a cosmic drama. We are the part of the universe that has become aware of its own biography. When we point a telescope at a distant galaxy, or decode the whisper of the cosmic microwave background, we're fulfilling a drive. A deep, fundamental drive, the drive to comprehend our place, to turn the void of the unknown into a narrative of breathtaking scale, of elegant physics, of inevitable wonder. Our search for origins and fate, it isn't a sterile exercise. It's how we weave ourselves into the fabric of existence. We take the chaos of creation and we find a story within it. A story that, for all its predictions of a cold and silent end, is currently ablaze with the light of understanding, and that light for now is ours to hold. The story of the cosmos is the ultimate biography. We've just read its pages from a silent point of infinite potential through the furious dawn of light and then the slow architecture of galaxies, all the way to this moment where we can look back and trace the entire arc. We followed the timeline to its quietest possible conclusion, a future of profound equilibrium where all stories end. But this is more than a chronology. It's the fundamental context for everything that is or was or ever will be. The scale is humbling. To see our brief, brilliant chapter set against that immense backdrop, it could feel diminishing. But the act of uncovering this narrative, it turns that feeling on its head. It becomes an act of profound empowerment. With nothing but observation and reason and shared curiosity, we mapped the history of existence itself. We connected the chemistry of our bodies to the furnaces of the first stars. We connected our moment of awareness to the deep time that made it possible. And that connection isn't metaphorical, it's physical. It's woven into the atoms we are made of. So when you look up at the night sky, you're not just seeing scattered points of light. You're reading a living epic. You're seeing the glowing aftermath of the Big Bang. You're seeing the vibrant cities of the stellar era. You're seeing the faint, redshifted signatures of a future already in motion. The story is still being written, and we are both its witnesses and its most curious characters. This journey reminds us that we belong to the universe in the most intimate way possible. And it belongs to us as long as we continue to ask and to look and to wonder.